Recording is rolling. It is Friday, February 7th. So yesterday I gave you guys a page of puzzles. It says chapter 13, and most of these are fluids questions. There is a a couple of thermal expansion questions. Okay, and then on the backside, we got a few more puzzles, boat puzzle, and a few other ones. Okay, so you guys got those? Okay. Now on your desk right now, and also uploaded to Google Classroom, I did give you guys a page of hints here. So question by question, there's some formulas. If you follow these step by step, it'll guide your thinking and lead straight to the answer. All right, here's like boat puzzle and type question there. Now, it's not the full solutions right now, but the equations you need are there and they'll guide your thinking. So there's still some critical thinking. So to review with you guys how to solve it, or at least the principles that you would need to solve all of these questions here. Okay. So, of course, we've been doing this last few days. You guys know Archimedes' principle tells you the magnitude of a buoyant force. Buoyant force wants to help you float, push you upward. Right? How much? It's equal to, in magnitude, the weight of the fluid displaced, which breaks down further like this: density of fluid times volume displaced times gravity field, like that. Okay, so then we go to that. One of the questions you guys are solving is like, what's the density of, say, this object for like this exact scenario like this, right? So if you see the scale drop off some number of newtons, that would be a weight difference, which would represent the buoyant force. So you got that. Okay. Once you know the buoyant force, if you know the density of water and gravity field, you can solve for the displaced volume, which would be the volume of the object if it's completely submerged. And then if you can figure out the mass of the object, divide by that volume, that would be the density of the object. So here's one of them. Boom, done. Okay. You guys know density is mass per unit volume. This is an intrinsic property of matter. So it doesn't matter how much of something you have. Like if you have a small lump of iron or a large lump of iron, it's the same density. The density of water is always 1,000 kilogram per cubic meter. That might be a really handy number today, right? Water density is 1,000 kilogram per cubic meter. Okay, SI units. Here's Archimedes' principle again, and here's pressure. Now these two formulas look pretty similar, right? Like buoyant force is density of water times gravity times the volume displaced, and pressure is density of water times gravity times depth. Right, so we got force and pressure, right? Similar looking formulas there. Okay. Here's a classic question. How much of an iceberg is submerged? Actually, this is exactly one of the questions you guys have today, and here's exactly the answer. Okay. Of course, I want you guys to ideally be able to solve from scratch. Okay, you guys got force equilibrium, and then there's chain of events and it leads to the answer that way. But that is the answer, right? What are your questions? The C tube is pretty fun. So I think the pressure is the same at some elevation within one liquid, right? So the pressure here are the same. But if you follow the arms up, like the left arm and the right arm, you get to the same pressure from two different stories. Okay, so you have to, I remember pressure was rho GH. So I have to add all these rho GHs and also consider if both ends are open to the atmosphere is pushing on both sides, right? Which does cancel out. I did that here, right? But step an equation that way, you can solve for like you know all the variables except for one. You could solve for what's the density of this gold liquid or something. Right? You could solve you know everything else. Pascal's principle: pressure is transmitted undiminished. So if the pressure is all the same as hydraulic fluid and pressure is force per unit area, that means with a small input force on a small area piston, you can lift a large output force on a large piston. That would be a hydraulic lift to give you a mechanical advantage, which is also exactly one of the questions that you guys are trying to solve today. Okay. Now, all these examples what we've done so far are working with stagnant fluids. So the fluid's just there, not really moving. Okay. Now, yesterday, I got more into, well, what if there is water flowing through a pipe? So now it is in motion. Okay. There's a pair of questions on today's page near the end that go hand in hand. Conservation of flow followed by Bernoulli principle. Okay, so these two kind of go hand in hand. Okay, so conservation of flow. I think the flow rate is the same all throughout this pipe system. Now, different size pipes means the water speed is going to be different. So you can handle it with this right here. Cross-sectional area times speed. That product is the same everywhere in the pipe system. So if you can figure out three of these, you can solve for the fourth. Okay. Your notes yesterday, we did some examples of that. Okay. This green box considers if you have a compressible fluid. So if you have steam going through here, you'd also have to consider the density. But don't worry about this green box so much. So I'll cover that one up. All you guys need is just this gold box right here. So for incompressible fluid. Okay. Now, once you know conservation of flow, you can figure out what's going on in terms of pressure with Bernoulli principle. So this fish floating around this pipe system, I think the fact that the fish changes elevation, that's going to change pressure. Like the internal pressure of the water pushing on the fish. Okay? But also the fact that the fish goes from a large pipe to a small pipe and therefore the water speeds up, well, that changes the pressure too, right? So actually in this one, there was also a pressure change. So can you navigate this Bernoulli principle, which we derived yesterday from conservation of energy? Do that. Okay. A couple of your puzzles involve ideal gas hall. There's like a chamber with a piston. Right? You guys see a couple of piston chambers. Right? So here's your guiding formula here. It's pressure times volume equals number of moles of gas times, some constant I'll call R times absolute temperature. Okay. So this relates pressure, volume, and temperature for gas. Now within that chamber that you guys are looking at, oh, actually got it right here. Okay. So here's your pistons chamber. Okay. There's some set amount of gas. So this N is a constant. Okay. If you really need a number to plug in, you can just plug in 1. Or you can say a 1 mole of gas or whatever. Right. This R is just a constant. So in terms of proportional change, it doesn't really matter what R is. So you can just call that 1 also. Right. So you're trying to relate what's the pressure, volume, and temperature of the gas. Now, one of these, number one, I changed the temperature, and I asked, well, what's the height change of the piston? So that's like it's really, you go through volume, but assume constant pressure on number 1, assume constant pressure. And the second one, you are changing the pressure because you're putting a big old weight on it. And you're looking for a volume change. So assume constant temperature on number 2. Okay. So between number 1 and number 2, each of those has only 2 of these variables changing. Right. Okay. Number 1, leave the pressure the same. So you're looking at for number 1, what's the relationship between temperature and volume? Number 2, what's the relationship between pressure and volume? Okay. Right. You guys get that? Okay. And how do you go from volume to height change? Say number 1, I was asking about that. Guys, could the cross-sectional area, like the circle area, times height, that would also represent the volume of the chamber, wouldn't it? Okay, that might also be helpful. Okay. And one more detail, because when I talk about a temperature change, say going from 0 degrees Celsius to 80 degrees Celsius, can you plug in to this formula? Oh, 0 degrees Celsius and for T. Can you do that? Is that a thing? Can you plug in a 0 for this T right here? 0 degrees Celsius? Does 0 go here? No. Guys, 0 degrees Celsius, what number actually goes in for T?
273.
273. Yeah. You guys know how to convert from Celsius to Kelvin? Okay. And you have to put Kelvin in for temperature because notice it doesn't just say temperature, it says absolute temperature. Right? You have to use Kelvin. So if I give you Celsius, very simply add 273. That's all to go from Celsius to Kelvin. Because otherwise they're scaled the same. So a temperature difference of 1 degree could be the same for both systems. Okay. But 0 degrees Celsius is 273 Kelvin. Okay. You guys got that? Okay. All right. All right. Good so far? You guys good? Okay. Then there are a couple of thermal expansion questions. So this here is linear thermal expansion. You heat up a material, it expands. How much? How much it expands is equal to the original length times coefficient of thermal expansion times the temperature change. And I told you guys the coefficient of thermal expansion, well, I printed it here, but the superscript didn't print very well. So use alpha equals 12 times 10 to the negative 6, and the unit is 1 over Kelvin. Okay. That's true for both steel and concrete. Okay. Now the concrete one is more like a block, so you have to think in 3 dimensions. Okay. Again, I gave you guys a bunch of guiding hints on this paper that's both printed in front of you on your desktops, but also this is uploaded to Google Classroom. Okay. So for the steel bridge, it's just a linear expansion, but for the block of concrete, which is the next question, think, well, I got a length, a width, and a height that are all expanding. Okay, so I have to consider all those dimensions. Right? All right. All right, so you guys got lots of hints. You guys got all the content you need. There's, of course, some good critical thinking here. If you keep a pretty good pace and you finish these by the end of class today, then you could turn that to the grade tray if you want to get off your hands. And if you don't quite finish today, then you guys can turn these in on Monday.